breakfast this morning. I just wanted to thank the conveners for organizing this workshop. I'm so excited to have a chance to be here and see all of you in person and to contribute to the discussions. And at the inspiration of the conveners, I've spent some time trying to reflect on what are some of the common themes or issues between subducting and rifting margins for my own work. And so I wanted to share a little bit of that today. And this work comes from so many collaborations and involves so many more people besides me, who I'll try and highlight as I go through. And in particular, from a number of fabulous graduate students I've had the chance to interact with over the years. But before I do that, I couldn't resist to have my own live Hawaiʻi for this meeting to add to Helen's. I appreciate the geographical non-discrimination element, but there's also so many parts of Hawaii that kind of have subduction-like or rift-like components. So the left-hand panels are showing the décollement that forms at the edge of the Hawaiian Islands as the volcanic edifice spreads out and overrides the oceanic plate. And some of the biggest earthquakes in Hawaii happen here. And if you look at an image like this, the upper panel from Julie Morgan, you could pinch yourself if that wasn't an accretionary prism of a subduction zone. And the lower panel is showing a recent seismic reflection image from just to the southwest of here from Bryan, Boston, showing another one of these features. And the Big Island also has magmatic rift zones. And so this is showing the the eastern side of the Big Island, and this green area showing the eastern rift zone associated with Kilauea. So anyway, I couldn't resist to talk about all the rifting and subducting aspects of Hawaii. Okay, on to the main part of this talk. So we can look at these two different systems, subduction zones and rifts, and obviously they're different in many ways. But a couple of the common questions we can ask about both of these places is how is deformation distributed in space and time? So in these two cartoons, hopefully you recognize the left one as a subduction zone. And so how is deformation occurring both on the megathrust, but in the overriding and subducting plates, and how does that evolve? And then the left-hand panels are showing kind of cartoons representing different stages in continental rifting and understanding how deformation is distributed in the upper part of the system across different fault zones, and how it varies with depth and how magma is involved are important questions we could ask there. And so kind of a common theme. And another one that's been alluded to a lot already this morning is what controls how faults slip. This is relevant to both subduction zones and rifts and many other fault systems, but we see all these different ways that fault zones can behave. And so what controls that? And so after reflecting on this a bit, the theme that I landed on was that was a kind of common set of advances and questions is of heterogeneity. And we can think for all of these systems that you have some combination of, these, as I put here, these fundamental geodynamical drivers or large scale rheology that is kind of the first order control on these systems. What are the plate tectonic forces involved? What is the large scale thermal structure and rheology of the plate or plates involved? Flexure, but kind of superimposed on that are a number of heterogeneities. We know that the Earth is complicated, and so the plates involved have a history that's baked in and influences later processes. And we also have other things that are varying, like surface processes. And so first, if you see this in many people maybe are starting to gag into your coffee, pre-existing structures, really? In many cases, when we see some way in which our study area deviates from what we expect from the things on the left here, it's pre-existing structures to the rescue. That must explain it. Or that in the worst case, it can lead you to say, every rift and subduction zone is special and different. And that also isn't a useful framework either. And so the framework that I hope to share with you is one in which we can better understand those heterogeneities and how they are superimposed on what we get from basic processes in a more predictable way. And so the lower panel is a really nice figure from a recent paper by Fagerang and Beal. And the middle panel is showing something I think Damien showed before, which is just how you expect for a homogeneous fault slope to vary with depth. And so in the shallow part, sorry, I can't see my pointer, so I've totally erratic pointing. But in the shallow part of that system, where you have lower pressures, maybe you would have stable sliding, but once you get to high enough pressures, but not too high temperatures, you could have something like stick-slip behavior and earthquakes. And then at greater depths, with increasing temperature, you would again transition to creep again. But that's for a homogeneous fault, and we know that they're not. And so in this system, the cartoon here on the left is showing some of the compositional heterogeneity and changes in width we might expect for a real fault zone, which don't erase that overall pattern, but they superimpose complexity onto it in important ways that we need to understand. And so I'm going to walk through some examples for you of how I think we've learned more about heterogeneities and how they influence these systems. And kind of one way in which I feel like we've had a chance to make progress on this is through the kind of studies that are in the spirit of GeoPRISMS and margins and other programs, but large multifaceted studies of focus sites. And so I have kind of 3 maps here showing the 3 areas I'm going to focus on for my examples. On the left is off of the Alaska Peninsula, and a number of data sets have been collected there over the years, and most recently the ACE experiment, a kind of onshore, offshore seismic array, which is all the dots here. The middle panel is showing a zoom in of the northern part of the Malawi rift system, where through Continental Dynamics program, we're able to collect a large multifaceted data set. And on the far right is the eastern margin of North America, where one of the major efforts was, again, the acquisition of a big onshore, offshore imaging data set. And these kinds of big studies provide a really important framework for imaging the configuration of plate boundaries like throughout the lithosphere. And so here's a cartoon of a rift system. And on the right are listing different kinds of geophysical sort of imaging data sets and how they can tell us about different scales. And so, of course, this isn't the only piece. Like, we really have to combine this and integrate it very closely with geology, geochemistry, numerical modeling, and experiments. But it's kind of one part that kind of provides a framework for some of the other pieces. And in addition to providing this kind of multi-resolution picture of plate boundaries, the acquisition of these data sets has had a couple other great legacies as well. And one is just a gigantic education, outreach, and partnership building component. I was kind of counting up, and I think it's literally hundreds of students and early career scientists who've been involved in both the collection of some of those GeoPRISM data sets and in training workshops that accompanied them. And this is the effort of so many people, including many people in this room, to facilitate that. Part of those efforts has involved short courses, and that's what the kind of middle lower panel there shows. They're the backbone for a lot of research projects that are done, and being in the field with others is also, and collecting these data is a great way to build different collaborations and relationships, and when it's done internationally with international partners. And so this is one really great legacy of these things. And they yield these data sets, which are, as I mentioned this morning, are open. And a huge way that happens is through facilities that actually archive and share these things in a good way. And even better, many of these take the PI out of the equation. Data goes straight from collection to the archival database. And so I think, especially for the raw original data, this has been so great. It'd be interesting to discuss if there are ways that we could share the data products from these things in a way that helps facilitate international interdisciplinary collaboration even more. So I just wanted to highlight those couple. All right, so now we're going to come back to this theme of kind of looking at how heterogeneities can be superimposed on basic processes to help us understand the systems that we see. And so I'm going to go through a few different examples here. And these are all my own bias of places that I've had a chance to work and think about. But we'll kind of step through each of these, and hopefully you can I can share with you some of what I think we've learned about that and hear from you. So for the first, we're going to talk about bending faulting in the subducting plate in the Alaska subduction zone. So in the kind of lower panel here is just our cartoon of our subduction zone. And one important thing that's happening is that this subducting plate is bending and going down the hatch. And as it does, you form extensional faults in the upper part of that system. And these are thought to be very important for as a way to bring fluids into that subducting plate and then bring fluids into the solid earth, where it can have a number of consequences. And so we want to know like what controls the extent of this faulting for a number of reasons. It creates roughness at the top of the plate, but also could facilitate changes in hydration. And so the Alaska subduction zone is kind of a nice place to think about this. So the figure on the right is just showing a zoom in of this area off the Alaska Peninsula. And hopefully you can see the colored contours are of the depth to the slab. And one thing that's happening here is that those contours are getting closer together as you go to the west. And so you have a more and more steeply dipping subduction slab. So you would imagine that just throwing away any heterogeneity, you bend something more, you're likely to fault it more and at the outer rise. The other thing happening here is that we have changes in pre-existing structures in the incoming plate. And so the kind of light shading there is showing magnetic anomalies. And so we imagine that or think that pre-existing, like our abyssal hills formed near the mid-ocean ridge would parallel the paleo mid-ocean ridge and thus these anomalies. And so you could expect that in the east or western part of our area, you might have kind of east-west oriented pre-existing fabrics, whereas in the east, they would be north-south. And so this kind of sets up a nice experiment for us. And the new data acquired through the Alaska Amphibious Community Seismic Experiment included beautiful bathymetry data that map a lot of the seafloor. And so now I'm sort of zoomed in on a little section of that. Here's the trench to orient you. And hopefully you can, and this is illuminated, but hopefully you can see all of this faulting in the incoming plate. And the yellow lines are showing interpretations of those faults. And I should highlight, this is all the work of Jake Clark, who's a current graduate student at NAU. And he's categorized these faults in many ways, like everything about them. Ask him, he can tell you. But one thing is their orientation and how that changes along the strike. And so each of these is showing a histogram of the orientations of these faults in comparison with the red line, the orientation of the trench, and with the gray bar and line is showing kind of the expected orientation of pre-existing fabric from those magnetic anomalies. And you can see that pretty much across the board with some interesting complexities, ask me about later, can't talk about now, you know, that it's really the pre-existing structures are having a big control in the orientation of these faults. However, if we kind of look at just the amount of faulting along strike, you know, again, using Jake's characterization of those of the bathymetry data, the red squares are kind of showing a sum of all the total amount of normal faulting as a function of longitude. And you can see that there's this sort of gradual eastward decrease or westward increase, if you like, in the total amount of faulting. You wouldn't get that if it was all pre-existing structures. And so, you know, what we kind of put this together to see is that you have a process of this bending and fracturing of the plate. And one of the first order controls is just how much you're bending that plate. But you're modulating that with pre-existing structures in terms of the orientations of the faults and maybe with some positive feedbacks. And so this is kind of the spirit of heterogeneity that I wanted to explore here. And so now we're going to kind of walk through kind of more complex examples. So we're going to stay with Alaska for a minute, but now consider, you know, multiple sources of heterogeneity that can conspire to influence the megathrust. So, you know, in these settings, we want to know like what, you know, what controls the properties and behavior of the subducting plate boundary. And, you know, it takes two to tango here. So the subducting plate is doing its part. It's bringing sediments and fluid and maybe heterogeneous structures into the subduction zone. And that's sort of illustrated in these cartoons here on the left by, you know, a thickness of sediment that's coming in, but also maybe topography created either well upward of the trench or by bending faulting. And those things could influence the homogeneity and properties of the plate boundary. On the other side, we have the upper plate. And there's a number of interesting recent studies that show how it could influence things. And and just in a more global way, we could imagine that with depth, you would have a more and more rigid crust that overlies the plate boundary. And that's shown in this very nice paper by Solaris and Renero. And so just that you have an increase in rigidity that you expect just from, increasing pressure of this crust at greater and greater depths. And so, how do these two things kind of work together? Because of course, we've just talked about the incoming plate is not just some, beautiful uniform thing, and neither is the overriding plate. And we're going to carry on with Alaska now with many more things on this map. So apologies, but it's an interesting place to consider changes in plate boundary properties and deformation, because we have changes in locking of the plate boundary. That's shown with the kind of purple to yellow colors, more locked to less locked. It's had a number of recent earthquakes, as highlighted earlier. There are changes in seismicity along strike. And so, within this setting, what influences those things? And so, in particular, we'll compare this area, the Smitty segment, more locked, more regular Great Subduction Zone earthquakes, with the Shumagon Gap, which seems less well locked and has more background seismicity, but fewer really large events. And on the incoming plate side, we know that I've kind of described to you this bending fault difference. So we can see a change along the subduction zone. We also have differences in the thickness of sediments that are coming into this plate boundary. And so, to the east, we have this much thicker pile of sediments that then are subducted and seem to, or some of which are subducted and form maybe a more homogeneous plate boundary. Whereas in the Shumagons, we have a much thinner sediment and a more faulted seafloor that could create a more heterogeneous plate boundary at depth. And so I've told you about the bending faults, but these changes in sediment thickness are like the accumulated differences in the surface processes over millions of years. I mean, part of this, what is subducting here, is a fan system, the Zodiac fan, which formed in the Eocene and Oligocene and off of northwestern US. And now those surface processes are having a role as that thing gets transported across the Pacific and is now subducting here. But you also have more recent climate-driven fluctuations in sediment entering different parts of the Alaska subduction zone. So a couple different sources of heterogeneity on that side of the of things, but also we see changes in the overriding plate. And so now these panels are showing a compressional wave seismic velocity model, and so the yellow colors are lower velocity and the oranges are higher, focusing on the overriding plate here. And overall, kind of like that example I showed before, we see this, a nice increase in velocity and presumably rigidity of the overriding plate with depth, but it's not doing so smoothly. You see, hopefully you can see, especially on my nicely annotated one, there's some kind of steps in velocity. And my co-authors and I infer that these might be related to contrast between terrains that build the overriding plate in this subduction zone. And so both the thickness of this crust and these changes in properties between terrains, when we compare them with reflection data and with seismic earthquake behavior, seem to control properties of the plate boundary. And so, so here we can kind of combine all those things to say, okay, we see these changes in inputs, and maybe they help explain some of the along strike heterogeneity that we observe in coupling and great earthquake history. And the overriding plate is kind of giving us down dip changes in behavior. And so, but with greater characterization of these things, we can see how both of those sources of heterogeneity are modulating the overall background, pattern of subduction zone megathrust behavior, and in a not overriding it, but controlling it and modulating it. Okay, and so the next example I wanted to show you was from the Malawi Rift, and this is a place where we I think is a nice example of different scales of heterogeneity, like finer scale and kind of lithospheric scale. And so the right-hand panel is showing the southern part of the East Africa rift system. Hopefully you can see all the black dots and beach falls outlining earthquakes occurring there. And I'm especially going to focus on the western, really can't point for anything here, the western and southern parts of this rift system. where it's a relatively early stage rifting. There are very large border faults with deep earthquakes that occur on them, active intra-rift faults, which are the, here's would be an example of a border fault in this cartoon, and you have these smaller faults like within the basin created by that border fault. And there's relatively limited volcanism, at least at the surface. And so two of the questions we ask ourselves is, how is strain distributed between the border fault and intra-rift faults? And what is the role of magnetism in a rift like this? And so first, we're going to take the faulting question. Through a number of studies over the years, we've really been able to improve our characterization of just the dimensions of the border faults. They're gigantic. They're among some of the largest in the world. The panel on the right is showing sediment thickness, and these dark black lines are showing these border faults. They're like 150 kilometers, 100 kilometers long, and have upwards, greater than 8 kilometers of total throw that's occurred on them. Mega. But nonetheless, like within the rift, through further imaging, we can characterize the degree, like total amount of inter-rift faulting. And we see that, there are no border faults. It's not like no 8 kilometer throws in there, but 3 kilometers. And so they're big and they're active. And from our work, we can see that they've had a significant contribution to rift opening. And so if we take a number of these parameters, they're kind of consistent with what we would expect for rifting in a strong lithosphere and for changes in rift maturity. So the dimensions of these faults kind of shown here. This is like from the work of Natalie Accardo, kind of an estimate of like the total kind of vertical offset or vertical separation on a fault. You can see they're really big. The middle panel showing a histogram of earthquake depths from work of Cindy Ebinger and colleagues. You can see they occurred at great depths. All of that is consistent with just a strong lithosphere. No pre-existing heterogeneity is required. The right panel is showing a comparison of the Malawi Rift with studies to the north in Tanganyika, and to the south in the southern part of the Malawi Rift, of what proportion of extension is being taken up cumulatively by inter-rift faults. And you can see a nice pattern from maybe less than 10% here in Tanganyika, something like 20 to 25 in the Malawi Nyasa Rift, and then even greater in the southern part of the Malawi Rift. And so again, those are patterns that are reflective potentially of changing rift maturity. No pre-existing stuff necessary, but in detail, those patterns of faulting are being modulated by different structures. So that existed in this lithosphere before rifting, long before, but Proterozoic Archean. So the right panel now is showing the dark gray are Archean terrains, and the colored areas are Proterozoic mobile belts. And the whole location and general orientation of the rift is controlled by where those Archean terrains are. So you have, in the particular area of our study, changes in the orientation of the rift as the rift bifurcates around these cratons. At a finer scale on the left-hand side, these are magnetic data analyzed by Fuller and Kulawale and co-authors, and they show that there's this pervasive fabric, just to the west of this northern part of the Malawi Rift, from a shear zone that's kind of oblique. And the kind of combination of these different scales of heterogeneity seems to be influencing cumulative fault patterns in the northern basin. And so now I'm showing these. So this is this big border fault on the east side, but all the colored lines. Oh, no. Wait for it. Did I talk too long? Did it shut me off?
It'll come back. It should.
Can you draw on the whiteboard, Donna?
Yeah, I got this.
I think it actually shuts off when it's been on for too long, is what I'm learning.
I think it's heated up with all that science. Hey, thank you. All right, and so yeah, what I wanted to point out was that here, these color lines are intra-rift faults in this basin. And the panel on the right is showing kind of along this rift, changes in the distribution of extension between the inner rift faults and the border faults. So the dark black line is showing, again, like a vertical offset on this border fault, a combination of the elevation and the lake thickness. And you can see there it's highest in this southern part. You really can't point where this thing's going to be. It's highest here in the southern part of the system. Whereas as you go north, and the orientation of the rift changes, and we have these fabrics that are oblique to the rift inner, we have more faults, more of the deformation is accumulated on these intra-rift faults with respect to the border fault. So both those scales of heterogeneity are influencing the distribution of extension in a more detailed way. And then the kind of second, as a part of this multi-scale controls I wanted to highlight are for, how about the role of magmatism in magma-pore rifts. So the most southern volcanism in the East Africa rift system is just north of the Malawi rift in the circled area. And we're going to look at a profile across the that northern part of the rift. And one of the things that we observe from scattered wave imaging in the upper left-hand panel is that the blue is showing us the base of the lithosphere, and the red is the crust. And we have much more dramatic thinning of the lithosphere than of the crust here. And that's something that's frequently observed in really magmatic rifts, where we can imagine you have a lot of thermochemical erosion, but has not been observed as much, at least to my knowledge, in less magmatic systems. And that result is consistent with work on gravity data showing changes in lithospheric thickness, where you can see these higher degree of thinning in the north. But if we look at seismic velocities, they show us that we have a little bit lower velocities below the rift, possibly telling us about a little bit of thermal perturbation or lithospheric thinning, but they don't allow for massive amounts of magmatism today. And so we can recall that, again, this rift basin is occurring within these Proterozoic mobile belts and actually at the boundaries between a couple of them. And so our hypothesis is that perhaps the compositional heterogeneity associated with those the sutures of between those belts might include material that would melt more readily than you might get around it. And so that you can have an ephemeral source of magmatism that could help weaken and do this thermal erosion of the lithosphere and thus prompt rifting and kind of explain this preferential thinning of the lithosphere we see. And finally, if I am going very long, sorry, these other examples have been like, there was some some lithospheric template, and then we did stuff in there, and how did it influence it? I think the Eastern North American margin is an example of kind of evolving heterogeneity, where each stage influences the next stage. And so here is a kind of reconstruction. Back in the day, we had Pangea or close to it, and the Eastern North American margin formed as we rifted that, but it occurred in stages. And so in this lower panel, these blue areas are showing rift basins along the margin, and they kind of record an early stage of extension. Then there was the Central Atlantic magmatic province emplacement, kind of illustrated here on the left, which emplaced over a very short time magmas over this huge area. And then later we kind of went on to continue extending and finally rifting this margin. And each of those stages kind of influenced the next. So, firstly, the purple lines here are showing us old Paleozoic sutures. We see that these early stages of extension really utilized those old Paleozoic sutures. So the bottom panel, this is work by Rachel Marzin, is showing crustal velocity structure, across one of the largest of these rift basins, the South Georgia Rift. And she observes a pretty sudden increase in thinning of the crust. And there's an associated, formation of rift basins, which occurs right at where one of this big red line, where this old Alleghenian suture was. And so that was one influence. This rifting happened from 230 to 205 million years. then we have the Central Atlantic magmatic province occurs. And what we observe is that although that was magmatic over a really large area, magmatic emplacement, you had more magmatism occurring where you had more lithospheric thinning from this first stage. So the left panel is showing sediment thickness of this center of sediment thickness. So you can see that those are thicker to the west and thus reflecting more lithospheric stretching. And if we look at velocity models across those two places, we see that you have a larger and thicker high velocity zone in the west and the east, reflective of more magmatic intrusions. And so that earlier, we have kind of these cascading influences. And as drifting proceeded, this kind of dance between magmatism and lithospheric thickness continued. And this is work that that's really wonderful from Ann Bissell and Brandon Shuck that I had no involvement in, but I'm co-opting for my story here. But what they are able to observe is pretty complex pattern of magmatism and stretching, where you have these higher velocities at the edge of the margin, kind of like our classic magmatic rifted margin, but then this very thin and heavily faulted crust, followed by a much thicker one. And then it's kind of the evolving stretching of and final rupture of the lithosphere modulated the magmatism throughout the entire rift story. And that if we look even today, that now this is a passive margin, right? Like all the action happened 170 to 200 million years ago. If we look at where earthquakes occur in the southeast, they also bear some relationship to some of these pre-existing structures. And so that kind of cascading inheritance is influencing things over the life of the rift. So those are just some of these examples, but I feel like we've been able to, with greater observational powers, to observe and to characterize those heterogeneities and the fundamental processes and how those heterogeneities actually are modulating those fundamental processes. And I feel like a real legacy of GeoPRISMS and other programs has been to kind of focus efforts in one place so that we could actually do that. And sometimes that's a funding focus, but also an intellectual focus, as Damien highlighted. And I think that the future to make progress on this, recognizing that these heterogeneities control so much of our systems, is even more tightly interwoven interdisciplinary efforts to span across scales and time. So thank you.
Okay, for the sake of time, we're going to save all the questions till the end, till the very end. So I'd like to welcome Zach Hunt. He's going to give a presentation on Not So Simple After All, Challenging Simple